Hi, my name is Sophie.
And my name is Sarah, and today we will be discussing submarines.
Let's dive right in.
First, we will be discussing the submarine's history and applications. Next, we will explain the physics behind submarines. And lastly, we will explore the future of submarines.
First, the submarine's history and applications.
The development of the submarine began in 1535 with the creation of the diving bell. Invented by Guglielmo de Lorena and Francesco de Marchi, the diving bell was built of either wood, glass, or metal. Diving bells sank as a result of the downwards force from the bell's weight.
85 years later, the next major invention in the development of the submarine was created, the drebel. To control the vessel, passengers inside would use oars to propel the boat forward. To cause the drebel to sink, weights would be placed inside to increase the total density, forcing the boat downwards.
Next, the ballast tanks were invented. Created by Giovanni Borelli, the first ballast tanks were goatskin bags filled with water. The filled bags would allow for the density of the boat to increase and sink below the surface.
Then, in 1729, Nathan Simmons invented a submarine that was capable of changing its volume to sink below the surface.
The last major development in the history of submarines was in 1963 with the creation of the diver. The diver was the first submarine containing an engine.
Since their invention, submarines have had a wide variety of uses, from military to tourism to research. Their uses in the military were first popularized in World War II and continues to be an important part of modern-day warfare.
They can also be used for ocean tourism. Some tropical countries, beginning in the 1960s, started to use submarines as a means to show off their ocean life and coral. And finally, they have also revolutionized deep-sea research. Submarines have opened up exploration of the ocean to upwards of 95%. Next, onto the mechanics and physics of how submarines work.
First, we will talk about the physics behind submarines. Archimedes' principle states that a body immersed in a fluid has an upwards buoyant force on it equal to the weight of the displaced fluid. Important to the functionality of the submarine is stability. When submerged, two types of displacement are of concern: hydrostatic displacement, displacement concerning mass and buoyancy balance; form displacement, which is displacements concerning mass in relation to the propulsion. To ensure that Archimedes' principle is satisfied, it is important that both these types of displacement are considered.
The second law is Boyle's law, which states that the volume of a gas at constant temperature varies inversely with the pressure exerted on it. Archimedes' principle is applied to the mechanics of submarines as seen in the ballast tanks, and Boyle's law is satisfied via the internal hull. Next, we will explore the anatomy of the submarine. The inner hull is located within the inner lining of the submarine. Next is the outer hull, which is the external layer of the submarine. Next, the diving planes, which are divided into two types, sail planes and stern planes, control the rise and the descent of the ship.
Next are ballast tanks, which are located between the inner and outer hull. Ballast tanks can be classified into two types, the main tanks and the trim tanks. The main purpose of the ballast tanks is to control the submarine's buoyancy and maintain a state called trim, in which weight is equally balanced throughout the whole ship. The main tanks are used to make major adjustments to the submarine's mass by pumping water and air through flooding holes and vents. The trim tanks help maintain a state of trim by making smaller adjustments by pumping water in and out of the tanks.
The ballast tanks allow for Archimedes' principle to be satisfied. Whether the submarine is floating or sinking depends on the ship buoyancy, which is controlled by the ballast tanks. A submarine resting on the surface has a positive buoyancy, meaning that it is less dense than the water around it and therefore floats. At this time, the ballast tanks are primarily filled with air. In order for the submarine to sink, it must have a negative buoyancy. This is achieved by filling the ballast tanks with water, making it denser than the surrounding water. Depth control is achieved by adjusting the water-to-air ratio within the ballast tanks.
The internal hull is constructed of thick, high-strength steel with a complex structure and watertight bulkhead, separated into several compartments. This allows for atmospheric pressure to be maintained inside the submarine and satisfy Boyle's law. This has two practical applications. One is protecting the crew from immense ocean pressure at extreme depths, and the other is insulation from the extremely cold ocean temperatures.
Now we will look at the future of submarines. The first possible way to improve submarine technology is through underwater detection capabilities. This is an important application for the military as it will allow for possible threats to security to be detected. This enhanced detection is possible through the use of lower frequency active sound waves, which can detect other submarines' wakes from short ranges.
A second possible improvement to submarines is very low frequency communication, which allows submarines to communicate at various depths beneath the surface. This method increases accuracy and is applicable to further ranges. Finally, submarines can use dedicated ballast tanks in order to achieve underwater hovering capabilities. Buoyancy control can be obtained by pumping seawater in and out of the tanks in order to achieve a state of hovering. This could save energy compared to the current technology of using thrusters to maintain a constant position.